Hello and welcome everyone. We are now in the second part of the part 2 series of this multiple linear regression model implementation, and I've already transformed the columns that I told you before. Like you can see, the seats column has been actually converted from categorical 2 to numerical 2, as we've learned from cylinders. And so the engine has also been converted. This is the engine column and this is the new engine column, where I have replaced 0 with every input of standard and 1 with every input of turbo. Now if you want to look at this logically and intuitively, what we are actually trying to do when we subtract one feature to avoid the dummy variable trap is that, for example, the engine column has actually two unique variables, standard and turbo. Now if we create two different columns for standard and turbo, it is going to be meaningless, because we are actually going to create a column of standard and put all zeros inside it, and we are going to put a column of turbo with all ones inside it. So we've actually created two new independent variables which are actually totally connected, because at all the places where standard column is going to be 0, turbo column is going to be 1. So that is meaningless. So what intuitively we must understand is that we must always keep one feature less, because keeping one feature less actually does not change the model's precision. It actually simply reduces the computational burden on the computer. And just to tell you about a few changes, as I suggested that we should remove all the rows which have almost similar data. Like you can see this column of engine location, most of the rows inputs are front and very few are at the rear end. So what we try to do is that we simply delete this row. And also the brand, because brand actually it does hold a real life value while you are analyzing data for different brands, because brand value also creates or adds a certain value to the price of the new vehicle. But presently, because this brand value has a lot of unique variables and we cannot actually create so many columns, it just makes the video very boring. So let's just simply delete this too. And let me remind you, you cannot delete the columns which you've actually used to reference and create new columns. So just to improve our visualization, we can simply shorten these columns because we need to keep it, but we don't need them to actually be that wide. So now we can begin. These are actually our independent variables from wheelbase to engine. These are our columns of independent variables. We can actually see these sets of columns are our independent variables, and our price column is basically our dependent variable. And now we can start implementing our linear regression model. Now what you can also do is that if you want to actually create the summary output right here, so that you can actually compare, it's okay, it's right, but what I suggest is that you should create another worksheet in Excel, so that you can actually create names for individual worksheets and try to start with backward elimination, and with every elimination you can keep track of how your accuracy of the model has changed. So moving on, let's simply go to the data analysis toolkit. We can call regression and let's select. So for the dependent variable Y, we are selecting all the rows of the column price. Done. Moving further, we are going to select all our independent variables at once, because let me remind you, what we are actually doing here is backward elimination. We are going to chip in all the variables together, all the different independent variables together, and then we are going to actually look at them individually by subtracting and adding a few variables. And this time the output range should be a new worksheet. Now it should not be a new workbook, because that will actually open another Excel application. So it should be a new worksheet, and you can actually also define the name of it right now, but we'll go with the default value. Labels must be selected as always, and let's do this. So you can see there is a new sheet created. It's named as sheet 2, and here it gives us our summary output with all the various parameters that we needed. And you can simply just expand the boxes which you want, expand the columns which you want to improve your visualization. And here it is. Now let me remind you, I asked you that the p-value statistic would be very efficiently used to analyze our data, and the adjusted R square, not R squared and not multiple R. Basically R squared is just a square of multiple R, but what we are going to actually use is the multiple R squared. This is the column which we are going to actually focus on, the adjusted R square value, which presently gives us a value of 0.75400. And just to save this, let me actually give you this setting. Now you simply name backward elimination all the independent variables, and this will remind you that this summary output is basically the backward elimination's first step, where you actually kept all your values. And now let me also tell you what a significance level is. Now significance level is basically the barrier that you set for your analysis, for your model, so that you actually do not cross this significance level in the meanwhile. And we are going to compare significance level each time with the p-value of each and every independent variable, and we are going to work through it. So for the values of p which are actually greater than 0.005, we need to actually eliminate those parameters because they are actually not significant. The values of p which are smaller than, let me write this so you can better understand and anchor to memory, p value greater than significance. If this happens, what you do is that you eliminate, and when p value is basically smaller than significance value, what you do now is that you keep that variable. So this was in short the actual meaning of why we are using significance level and then using p-value for it. So let's compare. Now p-value of intercept, well, intercept actually cannot be removed because it is basically a constant value, so you should not compare this with the intercept value, but you're going to check it with the base value. So wheelbase is 0.01, well, definitely smaller than what we wanted. Next, moving further, the length. Now length is 0.48. So let us first try to look at others, and then we'll come back to this and understand if we need to eliminate it or not. Now weight again has a p-value of 0.15, which is greater. Height again has a p-value 0.967, and horsepower, well, just be sure that you look at the whole value of the data. It is basically representing 3.05214 into 10 to the power minus 5. So it's a 10 to the power minus 5 value. It is very small, so we must make sure that we do not remove horsepower. Horsepower is really important. And moving further, now peak RPM, well, it has a value greater than the significance value. Mileage has a value greater. Mileage of highway has a value greater. Seats has a value greater. Cylinders has a value smaller, so we are going to keep cylinders. Hatchback smaller. Convertible greater. Wagon smaller. Sedan smaller. And finally engine greater. Now what you need to understand is first of all, intuitively, why there are some values which are actually greater. Now look at our data set first. When you look at your data set, you can see that wheelbase, length, weight and height, all of these four columns, what they basically indicate is the geometry of the car or the vehicle. This is typically specific to this data set, so you can have different kind of intuitions in different data sets, but for this data set, what you should try to understand is that you found that wheelbase, you can see here, the wheelbase was actually smaller, and the length, weight and height were actually larger than our significance level, so they need to be eliminated. Now why is this happening? It's happening because these four collectively define the geometry of the vehicle. So if one of them is very well defined, or one of them has a little accuracy in their data, we can actually eliminate the rest of these and basically understand the geometry of the vehicle based on one simple factor. So you can actually do trial and test, like you can remove the length column first, and then you can remove the weight column, then you can remove the height column. You can do all of these individually, or you might remove two of these columns first, then two of these columns next, and you can just create all your combinations that you want. But just for the simplicity of understanding, we are going to remove all these three columns from our data set. So just to make the model better, we are going to shift the wheelbase parameter by simply actually saying cut here, and after horsepower we are going to actually select insert cut cells. So what happened is that our wheelbase column was removed from here and it has been pasted here, and now we can actually shorten our length, weight and height columns. Now do not be confused with these hashes. They do not mean that your data value has been deleted. It's just for the simplicity of visualization. Now let's again implement our model, and this time we go do this again. Now input y range is already pre-saved in the regression model. We need to change the input x range, so we select this, and this time we select from wheelbase to engine, and we simply drag it along till the number of columns that we have, and now you can simply press OK. And this time the new worksheet should be another worksheet that you are going to create, and you can press OK, and here you can see another sheet has been created. Simply now improve your visuality, and here it is. Basically you should focus on actually trying to keep the p-value very defined and the regression static. Now let us look at the adjusted r-squared values. So we've got our next summary output. Now let me name this backward elimination, and what are the columns that we removed? The height, the weight and the length. So let us keep that to memory, and now let us look at our adjusted r-squared and r-squared values. Now let me tell you that there might be days when you actually try to improve your model but it doesn't improve sometimes, just because your common sense is actually not what drives the accuracy of the model. So looking at our model now, the r-squared value has definitely decreased because we've decreased the number of variables from 0.77 to 0.6, but what we notice here that our adjusted r-squared value has also decreased from 0.754 to 0.753. But just to notice what's important here is that by removing three independent variables, your adjusted r-squared value has actually decreased only by 0.1%. Your adjusted r-squared value was initially 75.4% and it is now 75.3%. So for removal of three independent variables, you only get decrease in adjusted r-squared value of 0.1%. Now that is actually a great removal or a great elimination, because those independent variables were actually contributing to only 0.1% of your accuracy, so they were well removed. Now moving forward, let's analyze again. Now let me remind you that our p-value or our significance value was 0.05. so looking at intercept, sorry, we don't look at intercept. Wheelbase 10 to the power minus 10, very fine. 10 to the power minus 6 horsepower, very fine. Now peak RPM is another factor which needs to be handled. Peak mileage at the city needs to be handled, mileage at the highway needs to be handled, seats need to be handled, cylinders don't, hatchback don't, convertibles need to be handled, wagon needs not be handled, sedan need not be handled, and engine needs to be handled. Now let's again look at our data set and try to use our common sense of why certain values are actually creating a problem. Now when you look at your last sheet, the first thing that you need to go ahead with is the peak RPM, the mileage of the city and the highway. So looking at your data set, you would apply your common sense and you would say that the peak RPM would mostly be related with the horsepower of the car, or like this RPM and this horsepower would actually lead to an increase or decrease in the mileage in the city and highway. So basically city and highway mileage are basically related in a certain way, because you'll always see that the highway mileage is always greater than the city mileage. So basically they have a relationship, not a very defined relationship, like you cannot say it in a way that city mileage is always 5 units less than the highway mileage, because that's untrue. There are variations, but in a certain fashion what you observe is that highway mileage is always greater than city mileage. So you need to keep sure that you deal with any one of these in the next regression model making. And horsepower and peak RPM, once you start comparing, basically looking at your last sheet, your horsepower is actually very small value, it need not be changed, but your peak RPM has a very large value. So let's try and eliminate peak RPM and any one of this city or highway mileages in our data set and again implement our regression model. So doing that, what we try to do is that we let our horsepower be there, and we try to actually cut this column, and basically let's keep it right here or anywhere you want. We just don't want them in the perfect selection. And highway mileage, well, I love highways, so let's just keep highways and not cities. Cities are very polluted and there's a lot of traffic most of the times, so I prefer driving in the highways. So moving forward, now let us start again implementing our regression model. Now data analysis. Now you need to also change. Now just to tell you that I've edited that part where I was actually getting an error, because what happened is when we tried to actually remove some cells or cut some cells from this place to this place, our actual orientation of this sheet shifted, and Y was initially in the T column and it shifted now to the R column. So when I was actually trying to press OK and get the model, it displayed an error that both of them should have the same range. So make sure you change it. I did not include it in the video because it was just going to waste our time. So just change that, actually take a Y range again, and now simply clicking OK, and here it is, our another set of analysis data, the summary output data. And what we try to do with this right now is that we again look at the p values and look at places where we were wrong. Now you can see that again from the initial 7.754 we came to 0.753, but now again we have a higher value of adjusted R square. We've actually reduced our independent variables and we are still getting a higher adjusted R square value. Well, this was what I was actually telling you in the theoretical concept. You can see that R square value has constantly decreased. The value of R square was initially 0.77, then it went down to 0.767, and finally it is 0.766, which is a 0.001 reduction in value, but still there is a reduction in value once we reduce the independent variables. But the value of adjusted R square has always given us a better prediction. You can see 0.754 converted to 0.753 and finally to 0.754 again. So we've actually increased the accuracy of our model. In fact, this value of adjusted R square is actually greater than the value of adjusted R square in the first total selection of backward elimination independent variables. So this is presently the best model that we have. Let's look at the p-values again. Intercept, no, we don't look at it. Wheelbase, yes, it's fine. Horsepower is fine. Now mileage has a little problem. Seats has a problem. Cylinders is fine. Hatchback is fine. Convertible is a little problem. Wagon, not a problem. Sedan, not a problem. Engine is a problem. So engine, as you can see, it has a really high p-value and we need to definitely look at it. And just to increase the speed of analysis, we are going to remove multiple independent variables of different kinds in this video. So we are going to remove engine first and we are going to see what adjusted R square value is. So moving on, let's remove engine now. As you can see, this time I have not selected engine in the X variable. Price column remains the same, the Y range. In the X range I have only selected till sedan and I am clicking OK now. And again, let's look at sheet 5 now. Now you're going to notice something magnificent. Once we've removed engine, the adjusted R square value of our model has now increased further. It has gone from 0.754 to 0.755. So we've now created a better model by actually removing engine. And now moving on, again checking with the p-values, nope, nope. Yes, this has to be dealt with. Mileage again. Seats, yes. We see cylinders is okay, hatchback is okay, convertible needs to be dealt with, and wagon is fine, sedan is fine. So what we need to look at this time is we need to change this convertible. Well, you must always keep in mind that there is a certain level of common sense that you need to apply in these places. Like the value of significance was 0.05 and our p value for convertible is 0.07, so that's a very small difference. So you must try to not remove these differences at once. You must actually try to remove the differences in a descending manner. So the differences with the highest value should be removed first, and you can see here that the value we now have is seats and mileage. So let's remove seats and mileage together and look at what our data set is giving us. So seats and mileage together to be removed. Now since we need to remove mileage and seats from here, we're going to select this column, we are going to cut it, and we are going to paste it right here simply, and then again we are going to select this column, we are going to cut it, and we are going to select insert it right here. So we can see that one of our columns is empty, so we delete that column. And now remember, we have to again select the y dependent variable, and finally let's get it quick. Let me do this for you. I'm actually trying to eliminate a few steps so that you do not get bored of the video, because honestly all the steps are mostly the same. You're not going to find much difference in those steps. You must only try to focus on the intuition of why we are doing something, why we are changing the variables we are actually. So finally we have now reduced our two variables of seats and highway mileage, and we've selected the rest of the variables. And remember to eliminate engine right here. Doing this, now let's click OK, and here we have our adjusted R squared value to look at, the summary output. Now this is a crucial part. You can see adjusted R squared value has decreased. It is 0.753 here, and it is actually was 0.755 here. So there is a mistake in our understanding. We have actually created something worse than it was before. And just to look at the p values once, checking, and the p-value looks fine. So this is what I was actually trying to tell you before, when I was telling you that we must try to sometimes not think about the significance value, we must think about the adjusted R squared values also. So p-value for the difference was actually very small, where it was like 0.07. Like we removed mileage of the highway and seats here, so 0.1 mileage highway should be included again and tested again for the model. So we try to copy this again, and we try to paste it somewhere over here. You can paste it anywhere you're already going to. You can actually insert copied cells, and you need to implement your model again. Now what you do is that you simply press OK, and you get another worksheet. And you can see you have your adjusted R squared value back. You have 0.754, which was actually is actually less than actually 0.755 which we obtained, but it is still not that less. It is 0.1% reduction in adjusted R squared values. And looking at the p-value again, the p-values are almost perfect. The mileage high is actually 0.144, which we actually needed to remove. And finally we are going to remove this, the convertible column, and this is going to be the final step of our implementation. And finally, I guess this should be our perfect model. Let's select data analysis, let's select input Y range. Our input Y range, see, this is where what it actually was, and this is what we need to do, change it to now. And make sure you always check that the value of X and Y has been properly maintained. So once you do this, once you remove the convertible column and you press OK, you finally have your model, which is for now the best model, because now it's back to 0.75, which was actually earlier to say 0.754, then 0.7535, and now we have our model for it to be 0.75 0.23. so it is actually a very small reduction, and all our p-values are where we want them to be. And you can actually remove the mileage high again and try to do it, but just for making the video perfect and the model perfect, let's actually do this. And you can see that the adjusted R-squared value is actually decreased by removing the mileage of highways. So we are going to actually not do this step. So finally, after adding back our highway mileage column to our model, we just go to a backward checking of how our model has changed since time. So we know that after implementing or after removing the mileage high column, our model's adjusted R-square value went down. So we are not going to do this. We are not going to actually remove mileage h, and we are going to keep it just the way we kept it in our sheet 8 or in our previous model. So the adjusted R-square value for that was 0.7523. Let us move back further and try to analyze a little more. So from 0.7523, we have here 0.7549, where we actually just deleted one column, and that was convertible. So convertible actually created a lot of damage to our model. So 0.7523 from 0.7549, so that's a 0.2% decrease in accuracy. So presently we are now going to focus on sheet 7 because that is what we were the best at right now. And moving back even further, we have 0.7535, which is actually less. So we've increased our efficiency with sheet 7 right here. Moving back further, we have finally another value of adjusted R-square that is greater than the future, which we did encounter while we was working with our independent variables. So this adjusted R-square value is 0.75542, and comparing with our last best sheet 7 of 0.7549, so there is not a great difference, but there still is a little difference. But once we do that, I think we should also compare with the p-values. So 3 values which were actually greater than our significance level. And in sheet 7, once we eliminated a few variables, there were only 1 and another 2 values which were greater than our significance level, but 0.07 is very close to our significance level, so we are not going to consider 0.07. So convertible is going to stay both in sheet 7 and in sheet 5. The problem here is with this mileage high and the seats column. So we don't have seats column here, and we have actually created not much difference between sheet 5 and sheet 7 of our analysis. So I guess we can take any of these for our model implementation. So if you want to actually reduce computation, we are going to choose the model with sheet 7 where we've actually eliminated seats, and if you want to choose a more accurate model, we are going to choose this model which actually contains the number of seats. Well, seats is a very easy data to avail, so I guess we are going to keep seats and get a better model. And finally, so sheet 5 is going to be our ultimate sheet, our ultimate model, and these are going to be our coefficients which we are going to use for this multiple linear regression model implementation. So this was a great time we spent analyzing and creating the building blocks of our association with data analytics. And let's move on further and let's make this very quick and get to the final rules and aim of this tutorial. And that's it for this Excel sheet we have right now. So let's say bye-bye to it. So now we are finally concluding our whole implementation and access to multiple linear regression model. So let's get with it quick. The 3 steps to the perfect taste. Well, we did all these 3 steps. We looked at the value of the adjusted R-squared, looked at the p-values of each independent variable and compared it to the significance level, and with respect to both of these parameters, we added or deleted corresponding columns with higher p-values and looked again at adjusted R-squared values and then added or subtracted the further values. So these were the basic 3 steps to the perfect model which give us the perfect taste of data analytics. And finally, finally, the aim was to balance the p values and the adjusted r squared parameter values. We used our common sense to understand the data and reduce some computational processing as much as possible, but we did not fall foolishly into the trap of removing important variables just for saving the computational time. Always remember to have a great recap to all your sheets, to all the places where you've analyzed by changing models, and finally you can create the model. This is our model. This is our model where you can actually understand intuitively where the things have changed. Intercept is not that intuitive, but what you should understand in other ways is, for example, let's look at this wheelbase. Now wheelbase adds a positive impact to our data set. Horsepower again adds a positive impact, but what is this? This is our mileage in the highway. Mileage in the highway is giving a negative impact. Well, we can understand it basically when we already know that the high priced cars basically do not have great mileages. So basically what our model understood is that if a car is having a high mileage, its price would actually be lesser than the car which is having a low mileage. Similar for seats, we know that two-seater cars are basically the cool ones, which actually price a lot. So increasing the number of seats also adds a negative impact to our data set. But then there are other variables like cylinder. The more number of cylinders, the high cost to your car. It's very obvious. And then there is the H variable. Well, H variable, it was for hatchback. Now hatchback basically is not such a good car. Like, you can imagine the cars which have the highest price, those are sports cars, right? So hatchback will obviously include a negative effect. But convertible, yes, they are going to be coming with high price tags, so they have a great deal of positive impact on our model. And then comes W. Well, W was our wagon, so wagon cars, nobody chooses them right now, so they are very much on the negative. And finally, the sedan classes, they do have a negative impact compared to the price of a car, but not so much. That is all that you need to know. That is all that you need to intuitively understand from the model, and that is what your model is actually telling you, the things with positive and negative impacts. That was it. We did a very good task making this multiple linear regression model. If you can, you should definitely try to make more accurate models, better models than actually what we've created together due to lack of time. And finally, this was fun. Good luck for your analysis endeavors. See you soon. Happy analyzing.